We're going to work through our Chapter 7 test review here. So make sure you follow directions on these first few. It says write each expression in exponential form. And what we learned here is we can take what's inside our radical, so 5, and it's going to be to a power. So when something has a radical, we can change it from radical form to exponential form. The index out here goes in the denominator, and then our power out here goes in the numerator. And that's it. The next one, and this is where I've seen mistakes because people don't follow directions. They try to simplify this, but you're just supposed to write it in radical form. So it's the reverse of what we did here. So we want a radical, and we want a 2 inside of here. The denominator is the index, and then the numerator is the exponent, and actually, according to this one, we can put the 5 out here. But we also learned that you can put the exponent in with the 2, so 2 to the 5th, and so maybe a better way of writing this is 4 to the 32nd power. But again, this isn't a simplified question, so really we're just going to leave it in this form or this form. The next several questions in this review simply say simplify. And so what we're going to do is simplify. We don't want any squares left in here because this is square root. So if nothing's written here, we know it's a square root. And what we do is we take our coefficient here and we factor it. There's different ways to think through this. Simplifying this first one, this is what we've been doing. We have 8 times 4, and then 8 we know by now is just 2 times 2 times 2, and 4 is 2 times 2. So 32 is 2 to the 5th power. And so over here, what we've been doing is we can write square root. We don't really need to. This 2 to the 5th, so 32 is 2 to the 5th, we want as many squares as possible. So we have a 2 squared. So that's using 2 of these 2s, so now there's 3 left. So we can write another 2 squared. And then there's 1 2 left. So we have 1, 2, 3, 4, 5, so 2 to the 5th. A to the 4th, I'm going to do the same concept, a squared times a squared. And the reason we're choosing squareds is because we have a square root out here, and square root is inverse with squareds. B cubed we can write as b squared times b. And c to the 4th we can write as c squared times c squared. As you get better at this, you don't really always need to write this out, but this is how we first showed it. So the square root of 2 squared is simply 2. The square root of another 2 squared is 2. So these get multiplied out here, remember. We can't simplify the square root of 2, so that's going to remain within a square root here. So we have a 2 here. The square root of a squared is a. The square root of another a squared is a. Square root of b squared is b. Here's a square root of just b, which we can't simplify that, so that stays in there. Square root of c squared is c. And another square root of c squared is c. And we would want to rewrite what's out here. 2 times 2 is 4, so we have 4a squared b c squared times the square root of 2b. And that is the simplified form. Over here for number 4, we have a cubed root. So instead of splitting things into squareds, we're going to split them into cubes. So first, though, we want to simplify this 54. 54 is 9 times 6, and so we have a 3 times 3 and a 3 times 2. So 54 we see is 2 times 3 cubed. And so over here we're going to put cubed root. Don't forget to put the 3 up here. We have 2 times 3 cubed. And again, similar to what we did over here, now we want perfect cubes. So this a, we can think of a cubed. Another a cubed, that's 6 a's, and then we have 1 left over. So a cubed times a cubed times a is a to the 7th. And now we're going to go ahead and think of this cubed root, or apply this cubed root. Cubed root of 2, we can't simplify that. Please don't forget this index. I know I just mentioned that, but we got a 2. cubed root of 3 cubed is 3. 3 cubed of a cubed is a, and 3 cubed of another a cubed is a. And then we can't simplify the cube root of a, and so our answer is 3a squared times the cubed root of 2a. So that's simplifying. Now we're going to look at adding and subtracting with radicals. Remember, in order to add or subtract, you have to have like radicals, which means the index has to be the same, and what's inside the radical has to be the same. And so we can, if we have that, we can almost think of these as like terms. So we have 2 of these plus 2 more of them minus 2 of them. So we have 2 root 3 plus another 2 root 3 minus 2 root 3. Well, that's 2 plus 2 is 4, minus 2 is back to 2. So our answer is 2 root 3. So not a lot of work to show there because we're just adding like ones. Over here, we definitely don't have like radicals. I didn't mention over here because it wasn't applicable, but before we even try to add or subtract, we do want to simplify each radical. Root 3 and root 2 can't be simplified, but the square root of 12 can. We've seen this enough. So we got 12 is 4 times 3, which is 2 times 2. So 12 is 2 squared times 3. And so we have negative 3 square root of 2 squared times 3 plus 3 root 3 plus 2 root 2. And we can bring out a 2. Square root of 2 squared is 2. So that's negative 3 times this 2 that's going to be coming out here. So we have negative 6 times the square root of 3 plus 3 times the square root of 3 plus 2 times the square root of 2. And these two are like radicals because they have square root of 3. So negative 6 plus 3 is negative 3 times the square root of 3. So we keep this the same. And then we have this plus 2 root 2, which we can't add because it's a 2 within the radical and not a 3. So there's the answer for that one. Our next couple, number 7, is still addition, but this time we have cubed roots. So again, we want to simplify our cubed roots. 81, we know that's 9 times 9, and each of those 9s is a 3 times 3. And so 81 is 3 to the 4th. Well, we're dealing with cubed roots, so we're going to write negative 3, and we're going to say, well, we have, don't forget that 3 there in the index. We got a 3 cubed times 3, because we're splitting up into perfect cubes, plus 3 times the cubed root of 3. And again, I should have mentioned we want to simplify first if possible, and that's what we're doing here. Cubed root of 3 cubed is 3, so that's going to come out and be multiplied by the negative 3. There are a lot of 3's involved in this question. So negative 3 times the 3 that's coming out is going to be negative 9 times the cubed root of 3 plus 3 times the cubed root of 3. Well, negative 9 times the cubed root of 3 plus 3 times 3 times cubed root of 3 is negative 6 times the cubed root of 3. That's our answer for that one. That's our last addition and subtraction one. Over here, we're multiplying. Anytime we do stuff, it is helpful to simplify first, especially if you see something like this. The square root of 4 is 2. So this is 2. So actually we have the square root of 10 times 5 times 2, which is 10, which we can't simplify 10. That's 2 times 5, so our answer is just 10 times the square root of 10. So it is helpful to scan through and see if you can simplify anything first. Next one, looking through, we can't simplify the square root of 3. So we just have to multiply this out using the distributive property or FOIL. So negative 1 times negative 3 is 3. Negative 1 times root 3 is minus root 3. Root 3 times negative 3 is negative 3 root 3. And root 3 times root 3 is simply 3. And just as a reminder, root 3 times root 3 is 9, which is 3. And whenever we multiply a square root times itself, it's 3. And it's that way because root 3 times root 3 is actually root 3 squared. And square root cancels with squared to be 3. So a couple different ways of looking at that. Now we look to add like terms. So we have a 3 plus 3, which is 3. Negative root 3 minus 3 root 3. Well, like this is a negative 1 root 3. So negative 1 minus 3 is negative 4 root 3. Over here at number 10, there's a couple concepts we can learn here or use here. In fact, I might just throw in another example after this because the first way doesn't teach or demonstrate one of the concepts I want you to see. But when we have a square root over a square root, just a single term, it could have a 2 out here or something out here, but no addition or subtraction, we actually can see if we can reduce what's within the square root. So does anything go into both 3 and 48? And if you try that, you'll realize 3 goes into 3 once, and 3 goes into 48 16 times. And so really we're left with the square root of 1 over the square root of 16, which works out really nicely because the square root of 1 is 1 and the square root of 16 is 4. So when you have something like that, you want to reduce and simplify, and we just get 1/4. I'm going to write in a 10b here because I want to make one up that we might see. So we might see something like 2 root 14 over the square root of 21. This will work to show what I want to show. So we look at this again. Within the square roots, 7 goes into both of these, so we can 7 into 14 goes twice, 17 into 21 is 3. So really what we're left with is 2 root 2 over root 3. Well, we are not supposed to be left with a square root in the denominator. The square root of 3 is not a perfect square like 16 was. So what we do is we multiply by a special form of 1, and that form of 1 is the square root of 3 over the square root of 3. That coming from right here. The reason that we do this is because the square root of 3 times the square root of 3 is just 3, which we mentioned over here, even the same number. You might have a 7 or a 9, or well, not a 9, that's a perfect square, or a 5 in here, so whatever that is. And in the numerator, we have 2. Square root of 2 times the square root of 3 is square root of 6. Also notice you cannot reduce 6 and 3 because 6 is within a square root and 3 is not. So our answer to 10b is 2 times the square root of 6 over 3. Number 11 actually turns out to be very simple because we want to look and simplify radicals first if possible. We can't simplify the square root of 3, but the square root of 25, that's simply 5. So we got the square root of 3 plus 4 over 5, and that's completely simplified. Root 3 can't be simplified, you can't add these together, and there's no square root in the denominator that we have to be concerned about. Number 12 brings us to another concept. There's a radical in the denominator which we can't have, but multiplying by just the square root of 5 here is not going to be helpful. So when there's two terms, something added or subtracted, what we do is we multiply by what's called the conjugate, and the conjugate is simply the same two terms except we change the sign in between. And so we're going to multiply by a form of 1, and that form of 1 is the conjugate of the denominator. We do that because when you multiply something in the form a plus b, so we're going to say this is a and this is b, times a minus b, you always get a squared minus b squared, which if you have square roots, you're just going to be squaring those square roots. I'm not going to take the time to show this right now why this works, but we have gone over that before. So here, 5 times 3 is 15, so we're distributing up here the numerator. 5 times negative root 5 is simply negative 5 root 5. And then in the denominator, we learned that this will be the first thing squared, so 3 squared minus the square root of 5 squared. Now 3 squared is just 9. Well, I'm going to rewrite the numerator, so we have 15 minus 5 root 5. And in the denominator, we have 9 minus square root of 5 squared is 5. And then we just finish that off. We got 15 minus 5 root 5 all over 4. If this 4 had a common factor with both 15 and this 5, we could simplify, but it doesn't, so that's the end of that question. All right, the next few questions are solving. So if we have a variable under the square root, we learned that we should isolate the square root, square both sides, and then solve. Question 15, I believe it is, we'll have 2 square roots, and we'll work through that when we get there. So number 13, we want to isolate the square root. So what we're going to do is we're going to add 3 to both sides. Isolate means get it by itself. So we have the square root of negative 10 minus n equals negative 3 plus 3 is just 0. Once we're down to a square root, on one side, we want to square both sides. We square both sides because the square root of something squared is just what's on the inside. So when we square this, we actually just get negative 10 minus n. And 0 squared is still 0. We can add n to both sides. It's probably the quickest way to solve this one. You could have added n, or added 10 and divided, but we got n equals negative 10. Now, whenever we solve a radical equation by squaring both sides, sometimes in there we could get extraneous solutions. So we do want to go back and check to make sure this works. So we're going to come back up here and we're going to think I'm going to put in negative 10 for n. So we have negative 3 plus this. Well, this is negative 10 minus negative 10. Minus negative 10 is positive 10. So negative 10 plus 10 is 0. So this whole part would be 0. The square root of 0 is 0. And negative 3 plus 0 is negative 3. That works. Negative 10 is the answer. So again, isolate the radical, square both sides, and then solve the remaining equation. Number 14, isolate the radical. Well, it's already isolated, so we can square both sides. Over here we have 8 squared. On the right, the square root and the squared cancel, so we have 8a. And we have a quadratic equation here. So remember, when solving a quadratic, we want to get all terms to one side. So in this case, we're going to go ahead and subtract 8a from both sides. Which will give us a squared minus 8a equals 0. And from here we need to factor. It's 2 terms. We actually notice that, well, first thing we always do in factoring is see if there's a common factor, and in this case there is. So we factor out an a. We have a times a minus 8 equals 0. So either a equals 0, or we think what makes this equal 0, so that would be a equals 8. Once again, we squared both sides, so we do want to go back and check our both solutions to see if either of them are extraneous. So putting in 0, forget the squared, that wasn't part of the original. Putting in 0, we have 0 equals the square root of 8 times 0. Well, 8 times 0 is 0, the square root of 0 is 0. That works, so 0 works. Try 8. Put 8 in for a, so we have 8 equals the square root of 8 times a, which we're plugging in 8. And the 8 times 8 is 64, the square root of 64 is 8. That works, so both answers are correct. So that's our answer. All right, number 15. Number 15 has 2 radicals that are not like radicals, so we can't combine them. So what we do on these is we want to first isolate one of the radicals. All right, we have to start by isolating one of the radicals. Otherwise, I've seen a lot of people make mistakes, square both sides and then square incorrectly. So we're going to isolate one of the radicals. It doesn't really matter which one. I usually try to pick one that's more complicated, like if there was one with one term compared to two, I would isolate the one with two terms, but these both have two terms, so it doesn't matter. So the easiest one is just to go ahead and add the square root of -3 minus 4a. So add the square root of -3 minus 4a. Be careful as you work through here. Don't forget any negatives. There's several of them. So when we combine these, we got -3 plus the square root of -3 minus 4a. On the right side, we're simply left with the square root of -3 minus a. So first thing we do, isolate one of the radicals. Second, now that one of them is isolated, we are going to square both sides. Be careful when squaring, especially the left side in this case, because there's a tendency just to do it really incorrectly. So let's walk through this. We're going to square both sides. So we square this, and we square this. Now on the right side, we just have a square root squared. So when we square just a square root, they are inverses of each other. So the square root cancels with the squared. So on the right side, I'm going to give myself a little bit of space here. We got -3 minus a. On the left side, squaring, this isn't just a square root, it's two things added together. So it's a binomial, so we're going to go ahead and multiply it by itself. And so we need to multiply that out. Right side will be -3 minus a. Left side, -3 times -3 is 9. So we're just doing FOIL here. -3 times this square root is -3 times root -3 minus 4a. Now we're to this term. We actually have another -3 times the square root of -3 minus 4a. And then multiplying these two square roots together, when you multiply a square root by itself, it actually just cancels the square root. So we have plus -3. I ran this too close here, -3 minus 4a, because a square root times a square root just gives you what's on the inside. We have some like terms to combine over here. We actually have a 9 and a -3, so that gives us 6. And over here, -3 and -3 is -6 times the square root. And then this minus 4a. Now, as we just take a second and look what we've done here, we isolated the radical, then we squared both sides, and that eliminated the radical right here on the right side. And now that we've simplified, we actually just have one radical left. So we're getting there. We had two radicals, now we're down to one radical. Now what we want to do is we want to isolate the radical again. So we're going to come back to this. If you still have a radical left, you're going to come back to this, isolate one of the radicals. There's only one, so let's isolate it. So we would subtract 6 from both sides. I'll put this in a different color just to see that our work here. So subtract 6, and then we also want to add 4a to both sides to help us simplify. Get that radical by itself. So on the left, we have -6 times the square root of -3 minus 4a. On the right side, we have -9 plus 3a. we want to isolate one of the radicals. I could say isolate the term with the radical because we have this -6 here. We could divide by -6 here. It would work out. We would have fractions. It might be a little harder to work with. Or we could just square it here, which is fine. We would have to make sure we square the 6. But there's one other option which I'm going to use. It doesn't always work, but I'm going to divide by a factor that goes into 6, 9, and 3. So what goes into all three of those is 3. So I'm going to divide both sides by 3, which will just give us some smaller numbers to work with. So this would reduce to -2. So we have -2 times the square root of -3 minus 4a. On the right side, this 3, we can think of it actually 3 under the 9, and it's a common denominator, so we can kind of think -9 divided by 3, which is -3, and 3 divided by 3, which is 1, or just 1a. Now that we've done that, we can square both sides again. When we square both sides, be careful here, this is -2 times this square root. We just have to think this squared goes to the -2, which is 4. And it goes to the square root. When you square a square root, it cancels. So we're just left with -3 minus 4a. On the right side, we're going to go ahead and multiply this out. -3 plus a times itself. We get 9 minus 3a minus 3a plus a squared. You can think through all those terms. It will equal this. On the left, let's go ahead and distribute. So -12 minus 16a equals, we have 9. Actually, let's put the a squared first here. A squared. These two are like terms, so that's -6a plus 9. And we have a quadratic. So when we solve a quadratic, we want to get all terms to one side, or set it equal to 0 is another way to say it. So we will add 12 to both sides. Its like term is 9, so we'll put it right with that. We'll add 16a to both sides. That leaves us with 0 on the left. A squared plus 10a plus 21. And since it's set equal to 0, we're going to try to factor it, which it does factor. If it didn't, we would just use the quadratic formula. So here we see 21, factors of 21 are 3 and 7. They do add up to 10. And so a is either equal to -3 or -7, what makes these things 0. We do have to go back and check because we squared both sides. In fact, we squared both sides twice, so we could get extraneous solutions. Let's plug in -3. Can we think through this? Putting in -3. So let's just try one at a time here. -3, and we'll put in -3. This would be -3 minus -3. Well, -3 minus -3 is -3 plus 3, which is 0. All right, so we get 0. Putting -3 in here, -4 times -3 is +12. So -3 plus 12 is 9. The square root of 9 is 3. 0 minus 3 is -3. So that works. Check for -3. Let's go ahead and try, just throw in another color here. We're going to try putting in -7. So -7 and -7. If you need to do this off to the side, that's fine. So we're forgetting this stuff for now. Let's see what happens with -7. -3 minus -7 is like -3 plus 7, which is 4, and the square root of 4 is 2. Putting -7 here. -4 times -7 is 28. 28, so -3 plus 28 is 25. The square root of 25 is 5. 2 minus 5 is negative 3, so that also works. And so those are the two answers. Takes a while, but you can get to the answer. Number 16 is a little bit different. The last three, we had variables under the square root. In this case, we don't have any variables under the square root. So a little different approach we'll take here. This is actually this is like solving linear equations, except there's this one extra thing, which we've mentioned. We're going to come here, and there's no radical variables under the square root. So when that happens, we want to get anything with x on one side and anything that does not have x on the other side. So in this case, we want to subtract 5 from both sides. 2x minus x root 3 equals 11 minus 5 is 6. And here's what's different. We can't combine these. They're both x's, but this one has a square root of 3 and this one doesn't. So if you cannot add the terms together because of square roots, what we do is we factor out the x, or the variable. In this case, it is an x. So we're going to factor out the x. So we have x times what's left over, 2 minus root 3 equals 6. And we want to get x by itself, so we divide both sides by 2 minus root 3. That leaves us with x on the left side because these cancel. That's what we wanted. X equals 6 over 2 minus root 3. Well, we can't leave it like that. There's a square root in the denominator. So we multiply by the conjugate, which we did earlier on this test review. So we're going to multiply both the numerator and denominator by 2 plus root 3. And our answer, we're working on simplifying, so it's 6 times both of these. So we're multiplying this whole 6 by the 2 plus root 3, so we have 12 plus 6 root 3. In the denominator, we learned that if we multiply a number times its conjugate, it will be the first thing squared, so 2 squared, minus the second thing squared, which is root 3 squared. And if we think through this, we got 12 plus 6 root 3 over 2 squared, which is 4. Root 3 squared is 3. And so this is 1. And so our answer is 12 plus 6 root 3. Again, these are different because there were no variables under the square root. So we got everything with x on one side, everything that didn't have x on the other side, factored out an x, and divided. And then we simplified our answer. The final part of this test is to graph square root functions. And so this same exact one will be on the test. We want to do the square root of x. We learned what this would look like, so we should actually just be able to graph it. It's going to be half a parabola pointing to the right. We'll do it just for this first one here, choose some points. Notice we can't put any negatives in there because we can't graph imaginary numbers. So we put in numbers that are easy to take the square root of. So 0, the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. You could throw in 9 here, although it's not going to be on our graph, but the square root of 9 is 3. And so you have 0, 0, 1, 1, 4, 2. So I'm just graphing these points. And 9, 3 would be about right here. And then we go ahead and put our half a parabola there. Got a little off on my drawing. That should be crossing there. But there is a sketch of the square root of x. And graphing number 18 is similar. It's the square root of x, but this negative 4 on the outside is going to move our graph down 4. So our starting point for this sideways parabola is going to be here. Again, if you want to, you can plug in a few points. We're taking the square root. We already know if we put 0, we get negative 4. Let's try 1. Square root of 1 is 1. Minus 4 is negative 3. Put in 4, because that's easy to take the square root of. Square root of 4 is 2. Minus 4 is negative 2. And if we want to, we can put in 9. Square root of 9 is 3. 3 minus 4 is negative 1. So we have, it was moved down 4. So it goes here. We have the point 1, negative 3. 4, negative 2. 9, negative 1. So it's the same shape as on number 19, but it is shifted down 4. And then our last one, we usually see this minus 3 on this side. It means the same thing. So it's going to be a square root function, so it's going to be this basic shape. It's going to be moved left 2, because we think what makes this 0? Negative 2 does, so we'll go left 2 and down 3 is going to be our starting point. Left 2 and down 3. We know this 3 here is going to make it steeper, and what we do is we plug in a couple points to see how much steeper. Again, we do want to use points that will be easy to take the square root of. So putting negative 1 in here works out well, because negative 1 plus 2 is 1. The square root of 1 is 1. Times 3 is 3. Minus 3 is 0. Remember, we moved this negative 3, so we don't use this. We move this negative 3 over here. So negative 1, 0. So much steeper on our square root function. What's another one? Well, 2 plus 2 is 4, so that's a good one. 2 plus 2 is 4. The square root of 4 is 2. Times 3 is 6. Minus 3 is 3. So we'll have the point 2, 3. You can try going a little further. What else could we put in here? Well, we could put 7, because 7 plus 2 is 9, and we can take the square root of 9. 7 plus 2 is 9. Square root of 9 is 3. 3 times 3 is 9. Minus 3 is 6. So we have the point 7, 6, and that's as far as we can go on this one. So let's see, can we graph this fairly accurately? Well, that wasn't a good start. So this problem is much steeper than the other others in 17 and 18, but there's a sketch of that graph. And that's it. So know those concepts for your test.